All right. So this is it until what day? Monday, whatever what day we're coming back. Couple things. I booked a COVID test just because, like I said, I'm going down to see my elderly father. So there's all kinds of COVID tests available. They're probably going to expire. So I'm going to walk up the hill. I'm going to walk in the hilltop to get a COVID test. And they're encouraging you when you come back for spring break to get a COVID test. But I don't know, if you want to get a COVID test before you go home, it probably won't be a bad idea. And I'll put a recording out there today. It's going to be on pH. So I think if I remember right, last semester I had like 3 calculators on the screen and all that. I think it's a pretty good recording. So I'll put that out there to make up for Friday, right? And then after break, I think it's like Wednesday that things are kind of due, like March 30th, I want to say. Wednesday's March 30th or something like that. Okay. So if I forget at the end, have a great spring break. Don't do what I did, and I just looked in my bag to pull out my calculator. I'm going to the airport, and I teach forensic science, and I got a bunch of bullets here for forensic science, so I'm going to make sure I take those out of my bag. Okay, so let's look at this, and then we'll see what you got for quiz questions. But this is the back side of the limiting problem, or we're burning butane. And this should all work out here. So I'm going to do the very bottom here, kind of like I did last time. So if we need to check out how many grams of total product that we got out of this, and then how many grams of reactants reacted. So my total grams of product. The total grams of, well, first of all, what is the answer to the last question? I have students calculate this for 10 minutes. And the answer is how many grams of the limiting reactant left over? It has to be 0, right? It's a limiting one. There's no limiting left over. So let's see if this works out perfectly like before. The total grams of product is 1,068.3 grams. Total grams of product produced. 1,068.3 grams. Now that should match how many grams of reactants reacted. Now, first of all, the limiting one is all going to be gone. So our limiting here is C4H10. And that was 232.56 grams. That's what we have. So we know that goes into the 1,068.3 grams for sure. It's living. Now, plus the excess, we started with 960 grams minus how many grams we had left over was 127.7 grams. So this is the O2. This is the start grams. This is left over. So of the reactant in excess, if we subtract this out, I think we get 832.3. And if we add that up, it's pretty close. We're not quite perfect due to sig figs. But that does come out to be 1,064.8 or something. 1,064. That's off more than I figured. 832. It's off more than it should be. And I better double check my numbers. Anybody else have different numbers? 127.7 left over here? Anybody else have 127.7 left over here? Maybe I did this too fast. 3.99. Double check. Yeah, 127.7, that's right. I'll have to double check. It's off by like 4 grams, but that still might be right with sig figs, especially this 960 here. That's 3 sig figs. Okay, now how about quiz? On the quiz, we were doing through 14, 12, so we only added 12, 13, 14. And 12, did anybody work out 12? Tell me somebody worked out 12, because I made this problem up. It took me a long time to come up with these numbers. Somebody work out 12? Nobody in here worked out 12 yet? I guess we'll have to see if it works out. I was hoping somebody could say, yeah, I worked it out, it's spot on. Well, again, it took me a long time I actually had to make all these numbers up. Okay. Well, we left off with molarity. So let's review molarity again. So for molarity, we know that we are going to dissolve grams in solution. And the grams is converted to moles. So when we do the stoichiometry for this towards the end, it actually makes it easier because it's already in moles. So we don't have to use the periodic table. We don't have to look up any atomic weights. So to do the stoichiometry using molarity, it's actually easier. So there's different size volumetric flasks. Again, they're very, very accurate. We fill them to the scratch mark here. So let's look at where we left off. And we left off well, we did the first 2 molarity examples down here. So what is molarity again? It's moles per liter of solution. Moles per liter of solution. So let's go to the next page here, page 9. So just a couple more molarity ones. How many grams of NaCl? So if we pour out This would be 250 milliliters, right? 250 milliliters. If we poured out 250 milliliters or added 250 milliliters for a reaction, and it's 5.3 molarity, how many grams of NaCl did we pour out or did we add? Remember, it's liquid grams. So again, we're going to call this in the lab 250. Then I'll have to put a dot there to say that that one is a sig fig, or that 0 place, sorry. So how many grams? Now, molarity here is a double unit number. So it's back to the single unit number and the double unit number. So that molarity right there means you have 5.30 mole of NaCl in every liter of solution. So we have to get grams. How many grams? And we have to get grams. We know if we get moles, we can get grams. So the solution technique, again, most instructors are going to give you a formula for this, which is just mind-blowing to me. Start with a single unit number, which is the liters, right? So we're going to start with the liters. So we have 0.250 liters of solution. Then, can I bring in my double unit number as is so that liters of solution cancel out? And I can, right? I'm going to just bring this in just the way it is. So I've got 5.30 mole of NaCl per liter of solution. And my liters of solution, of course, cancels out. And if I'm looking for grams, we're going to convert moles to grams. We have 1 mole of NaCl. How many grams? How many grams? What's the molar mass there? 58.45? 45? All right, 58.45. So grab your calculator. And if everything's in the numerator, it looks like we get 77.4. 77. Okay. So we get 37.4 grams. The next example is going to basically be, it is the same solution technique. So in the next example, what mass? So we're going to be looking for grams of Ki, what we have to dissolve to make 325 milliliters of 8.23 times 10 to the minus 5 molar solution. Again, we're going to start out with a single unit number. And let's put this into liters. So we're going to start out with 0.325 liters of solution. And then we'll bring this in just the way it is. But let's convert that. Let's take that out of scientific notation. So if we take that out of scientific notation, 0.0000823 mole of Ki per liter of solution. And liters of solution cancel out. And we got to get grams, so we're just going to go mole grams now. So 1 mole of Ki, how many grams? How many grams do we get here? 166.00. Wow, nice. 166.00. Our moles cancel out. And if we run that through, we get a very small number. Uh, 0.00444. Ooh. So we get 0.00444 grams of Ki. Okay. So the next problem, we're just calculating concentration, but then it asks for the ions. So this is similar to lab. So it wants the concentration. There was a lab problem. It wants the concentration of sodium carbonate. It wants the concentration of sodium ion and CO3 2- ions. So the first thing we got to look at is if this becomes a solution, this is aqueous. And we're going to dissolve this solid up. It's going to become an aqueous solution. Now, the solution is going to be labeled Na2CO3 aqueous then. So in lab this week, I think you need 5 molarity HCl. But the H and the Cl are going to be split up in there. Just like this, the sodium and the carbonate are going to be split up into 2 sodiums and 1 CO3 carbonate. So let's see if we can figure this out here. We need moles over liters. And when we get all done, again, we're gonna have a bottle, a jug, whatever, with a concentration on it. And it's going to be some molarity, Na2CO3. But if this is an aqueous solution, the sodium and the carbonate are not hooked up in solution, right? We talked about ions and net ionic equations. It's going to be labeled that way on the jug, but they're not going to be hooked up. So let's see what we get for a concentration. We're going to start out with grams. If you're given grams, convert to moles, and then go from there, right? If you're given grams, convert it to moles. So we have 25.3 grams of sodium carbonate. One mole of sodium carbonate, grams. And the grams is 2 sodiums, 1 carbon, 3 oxygen. What do we get? 106.01. 106.01. 106.01. We're looking for a concentration. We want moles over liters. So we're just going to draw a line right here. We got the moles, right? Because our grams cancel out. We've got the moles. Let's draw a line and put our liters in the denominator. And our liters is 250 milliliters. Like 250 milliliters, 0.250 liters of solution. Right? Moles over liters doesn't have to look pretty. 25. 0.955. We round it to 3 sig figs, 0.955. 0.955. So 0.955 molarity. It would be labeled again Na2CO3. But we know inside there is 2 sodiums floating around for every 1 carbonate, right? We get 2 sodiums. So the molarity of sodium is going to be 2 times 0.955. So for sodiums, we're going to have 1.91. Remember, this is moles per liter. Moles is just a number, right? Just like a dozen is 12, moles is just 6.022 times 10 to the 23rd. Then you only get one carbonate, so it's going to be 0.955 molarity carbonate. Okay. Now, the next example just is a dilution. So if you have a more concentrated solution, but you don't want that much of a concentrated solution, it would make sense that you can just add water and dilute it down, right? So these next ones sound complicated. The book makes it a little bit complicated, but it's really simple. It's just this formula right here. I think your book uses a 1 and a 2, but that doesn't, let's just identify them. This is the molarity of the concentrated times the volume of the concentrated equals molarity of the dilute times the volume of the dilute. It's that simple. Perhaps you've diluted cleaning agents. If you ever buy a gallon jug of simple green, it's like $10. And you can dilute the simple green for everything. All you're doing is adding water. So let's look at this. So we have 0.850 liters of 5 molarity copper 2 nitrate is diluted to 1.8. This is the volume of my dilute, right? It's asking for what is the molarity of the dilute. Then this is the volume of my concentrated, and this is the molarity of my concentrated. So my molarity of my concentrated, the volume of my concentrated equals molarity of my dilute, volume of the dilute. And we do not have to switch units to milliliters, liters, whatever we get for volume, as long as they're the same. By that, if you have milliliters and milliliters, that would be fine. They're going to cancel out. So what are we looking for? We're looking for molarity of the dilute. So math-wise, I divide both sides by volume of the dilute, right? So I'd end up with molarity of the concentrated, volume of the concentrated, divided by volume of the dilute. Would be my molarity of my dilute. So 5 molarity times 0.85 liters. .850 liters over 1.8 liters. And liters cancel out. And we get 2.36. 2.36 molarity. Okay, this one. So we can already look. This is 1.59 molarity. Just look at this is 0.1. This is molarity of the dilute. This is molarity of the concentrated. Just looking at this, right? So what volume of 1.59 molarity? This is molarity of the concentrated. We're looking for the volume of the concentrated just by reading that right away. So we want to prepare 5 liters of 0.1 molarity. So this is the volume of my dilute. And this is the molarity of my dilute. So we want to take some of the concentrated, water it down, right? So we end up with 0.1 molarity. And if I solve my equation to get volume of my concentrated, I'm going to divide both sides by molarity of concentrated. So I'm going to end up with volume of my concentrated equals molarity of my dilute, volume of my dilute over molarity of my concentrated. And if I plug this in, we've got 0.100 molarity. Liters, 1.59 molarity. And we get 0.314 liters that we would take out. Okay, I'm going to skip the pH because we're talking about molarity and stuff in your book. I don't know why they throw pH in the middle of this. It doesn't, I just don't get it. So we are going to go to where they actually do the next section, 4.7. So 4.7 stoichiometry of reactions in aqueous solutions. So let's see what we got here. This is from 4.9 in the book. Metallic zinc, and this would be a single replacement reaction. Zinc is going to replace hydrogen. What volume of 2.5 molarity HCl? 2.50 molarity. What volume? Either milliliters or liters. Remember, we're going to do moles underneath, right? We're going to do moles under here. It's all the same yet. In milliliters is required to convert 11.8 grams of zinc completely to products. It is the same solution technique. We're going to convert grams right here. This is the only thing we're given to convert to moles. Grams, let's convert to moles right here. So we've got 11.8 grams of zinc. And from the periodic table, we've got 61.9 0.41 grams of zinc. 1 mole. So my starting moles, 0.180? No, 0.180. Okay. So again, there's nothing different here, 0.180, and that's in moles. Now the question is, we do the same exact thing that we've been doing. How many moles of HCl do we need to use up the 0.18 moles of zinc? And the mole factor fraction is 2/1, right? 2/1. So this, of course, is 0.360. This is in moles, right? We know this is in moles. We know that this right here is, this means 2.50 mole of HCl per liter of solution. That's what that means. I already know this is moles. This is moles of HCl. We only put moles down here. So now my question is, I need to get milliliters. If I get liters, I can get milliliters, right? So we're back to the same scenario. This is a single unit number. This is moles. This is a double unit number. Can I just, and I'm going to put mole down here. Can I drop this down as is? Can I go 2.5 moles over liters of solution? And I cannot, right? Because I can't go moles times mole. I did have a mole squared over liters, correct? So we're going to do this. We're going to bring this down and we're going to just flip the units. We have to flip the units. We have to get moles down below. So when we flip this, we are going to end up with 2.50 mole of HCl per liter of solution. Let's do one quick shortcut. Let's just cross out liters. How many milliliters in a liter? 1,000 milliliters, right? Let's just take this quick shortcut, cross out the liters and write in 1,000 milliliters, same thing. It saves us a step. So grab your calculators and we've got 0.36 at 360 divided by 2.5, 144 milliliters. So we end up with 144 milliliters of HCl. Remember, that is grams. We could have converted everything to grams, but if we dump in 144 milliliters of 2.5 molarity HCl with this chunk of zinc sitting in a container, you're going to do a reaction with zinc coming up. all of this should be gone, and we should just have these two products. That's what we just calculated. If we dump in 144 milliliters of HCl into the container that has 11.8 grams of zinc, all of the zinc is going to be gone. All of the HCl should be gone, and we're just going to have these two products. Okay, here's, I guess I label it a not so ugly owl. This is copied word for word. And it wants to know this. How many grams of copper 2 hydroxide will precipitate when excess sodium hydroxide solution is added to 53 milliliters of 0.572 molarity copper 2 sulfate? So what we're saying again is there's excess of this. We do not have to worry about it running out. But what do we have to do? We have to get moles here. We always get moles. So to get moles, again, I say this is a little bit easier because we don't have to look at our periodic table to start this problem at least. This is 0.0530 liters of solution. We got to get moles, right? We got to get moles. And then here, it is 0.572 mole per liter of solution. So that gives me my starting moles. And if I keep an extra sig fig did this, my starting moles is 0.03032. Again, the solution technique is exactly the same. What are we going to do now? Because we got to get grams right here. We have to get moles. How many moles of copper 2 hydroxide are we going to produce? My mole factor fraction, 1/1. We are going to produce 0.03032 moles. And then again, the solution technique is the same here. We are going to go 1 mole to grams. So 1 mole of copper 2 hydroxide to grams. Still on the screen, yes. And the molar mass is 2 oxygens and 2 hydrogens, right? 2 oxygens, 2 hydrogens, and a copper. What do we get for this? All right, 97.57. So we get 2.96 grams of copper 2 hydroxide. So on this quiz, we can now do 15. And there's kind of a limiting problem on here. You can wait. So 15, I'm only adding 15 from the quiz, and then see what you can do with some of the owl stuff. And then the recording is going to be all about pH. Okay? All right, have a great spring break, everybody. You deserve it.